I want you to imagine, just for a second, that you are holding a simple, humble compass in the palm of your hand.
Like one of those little plastic ones you maybe played with as a kid.
Yeah, exactly. You've probably seen one before, maybe held one on a hike. So you're looking down at it, and there is that little magnetic needle, and it's trembling.
Mm-hmm.
It swings around, hesitating for just a moment, and then it finally settles to point perfectly north. We are so used to this phenomenon that we barely even question it.
Right, we just take it for granted.
We really do. But, what is that tiny piece of metal actually responding to?
Well, it's easy to assume the needle just, inherently knows where north is, or that it's being pulled by the North Pole itself.
Right, like a giant magnet buried in the snow up there.
Exactly, but it's responding to something far more complex and, frankly, much more violent.
Which is exactly what we are exploring in today's deep dive. We're looking at Earth's magnetic field. It is this invisible, silent force, and as we're going to see, it is likely the very reason life actually survives on our planet.
It's the ultimate planetary shield, yeah.
It is. So our mission today is to take our time, assume you have no prior science background, and just unpack the actual mechanics of this shield. We want to make the invisible visible. So, okay, let's unpack this. We have this compass needle pointing north. What is it actually communicating with?
It is communicating with an active, churning engine thousands of kilometers below us.
Thousands of kilometers. Wow.
Yeah, when you hold that compass, you aren't just reading some localized magnetic pole. The compass, the trees outside, the whole atmosphere.
Inside it.
Exactly.
Huh.
You are standing entirely inside a massive, dynamic magnetic field generated by the Earth itself. The entire planet is basically behaving like an enormous electromagnet.
Which is just wild to think about because the field isn't just a static property of the rock we're standing on. It's a living system, in a way.
It's constantly moving, yeah.
So to understand that trembling needle in your hand, we have to look past the crust and travel straight down to the very center of the Earth.
Right, because if we want to understand where this magnetism comes from, we have to look at the Earth's core. And the architecture down there is just fascinating.
Okay, set the scene for us. What is it like down there?
Well, right at the dead center, you have the inner core, which is a solid sphere of iron and nickel.
Solid. But isn't it incredibly hot?
Oh, it is. The temperature actually rivals the surface of the sun. But the pressure is so unimaginably intense that the metal literally cannot melt. It remains solid.
Wow. Okay, so we have this super hot, solid iron ball in the middle.
Exactly. But surrounding that solid center is the outer core. And this is really where the magic happens.
And just to clarify for everyone, when we say outer core, we're talking about the deep layer surrounding the center, but the pressure here is a bit lower.
Right. The pressure is just low enough that this superheated metal is in a liquid state. It's basically a boiling, turbulent ocean of molten iron and nickel, and it's roughly 2,000 kilometers thick.
2,000 kilometers of liquid metal. That is terrifying and amazing.
It is. And that fluid dynamics aspect, that's the critical piece of the puzzle. This molten metal is in a state of constant, violent motion, primarily driven by heat.
Because the inner core is heating it from below.
Exactly. The inner core radiates immense heat into the bottom of that liquid outer core. So the metal at the bottom heats up, becomes less dense, and naturally rises toward the cooler mantle above it.
Like a hot air balloon.
Right. And once it reaches the top, it cools down, becomes denser, and sinks right back down.
Okay, that's essentially the same principle you see in a pot of boiling water on a stove, right? Just rising and falling.
Yes, thermal convection. But, if it was just rising and falling, we actually wouldn't have a magnetic field.
Oh, really?
Yeah, we have to introduce the rotation of the Earth. Because the planet is spinning. These massive rising and falling columns of liquid iron, they don't travel in straight lines.
Oh, of course. The spin twists them.
Exactly. They get twisted by the Coriolis effect. That's the same physical force that causes hurricanes to spin into massive spirals in our atmosphere. Down there, it's twisting these columns of liquid metal into massive corkscrews.
That is incredible. A planetary washing machine. So we have this twisting, rising, falling liquid metal. How does that make a magnet?
Well, what's fascinating here is how this movement translates into electromagnetism. We're talking about a process called a dynamo.
A dynamo. Let's define that really quick. That's basically a colossal natural generator that creates electric currents and a magnetic field, right?
Spot on. In physics, if you move an electrically conductive material like liquid iron through an existing magnetic field, it induces an electric current inside that moving material.
Wait, that brings up a bit of a chicken and egg problem, doesn't it?
How so?
Well, you need a magnetic field to create the electric currents, but you need the electric currents to generate the magnetic field. So, like, where did the very first magnetic field come from?
Ah, that is a great observation. The general consensus is that when the Earth was first forming billions of years ago, there were these trace background magnetic fields already present in the solar system.
Oh, just kind of floating out there in space.
Yeah, just weak fields. And the newly forming churning core essentially caught and amplified those weak background fields.
Okay, so it booted up the system.
Right. And once the electric currents started flowing through those twisting columns of molten iron, those currents generated their own much stronger secondary magnetic fields. It becomes a self-sustaining feedback loop.
I love that. Let's use an everyday analogy here to make it super clear. It's not a giant bar magnet down there. It's kind of like swirling a hot cup of coffee that's the motion while rubbing a balloon on your hair for static
Yeah.
electricity.
That's a fun way to picture it, yeah.
Or mechanically, it's like a bicycle dynamo. You
Yeah.
pedal the bike, a wire moves past a magnet, and it powers your headlight. The Earth is doing the exact same thing, just replacing the wire with billions of tons of swirling liquid iron.
Precisely. The mechanical motion is the engine. The field is just continuously regenerated by that relentless churning.
So when you look at that little plastic compass in your hand, you're essentially sensing the physical flow of molten iron thousands of kilometers beneath your feet.
Yeah. If the core cooled down, and the liquid metal stopped moving, the dynamo would just shut down.
And the field would disappear.
The magnetic field would just fade away completely.
Wow. Okay, so what does this all mean for us? We have this colossal electromagnetic generator running deep underground. Why does it matter so much to us up here on the surface?
Well, to answer that, we have to move from the crushing pressures of the core all the way out into the vacuum of space.
Right, out into the solar system.
Yeah, because out there, the magnetic field essentially acts as the bouncer for the entire planet.
Mm-hmm.
And it's a highly active bouncer at that.
Keeping the bad stuff out.
Exactly. I mean, we naturally think of the sun as this, benevolent force. It gives us light, warmth, energy for plants.
A nice sunny day at the beach.
Right. But the sun is fundamentally a massive churning ball of plasma. It doesn't just radiate light. It violently ejects physical material.
You're talking about the solar wind. Let's make sure we define that.
Yes. The solar wind is this continuous high-speed stream of charged particles blowing out from the sun in every direction.
And it's made of plasma, right?
Correct. Now, plasma is a state of matter where the atoms have been superheated so much that their electrons are literally stripped away.
So they become electrically charged.
Exactly. So what's actually hitting us isn't just a gentle breeze of gas. It's a relentless blizzard of highly energetic charged particles, mostly protons and electrons, and they're traveling at hundreds of kilometers per second.
Hundreds of kilometers a second. So
Yeah.
if those charged particles were allowed to just, smash directly into our atmosphere, the results would be pretty bad.
Oh, it would be devastating. It's a process called scuttering.
Sputtering. That sounds like a car engine dying.
It kind of is. For a planet, think of it like microscopic billiards. These high-energy solar particles crash into the oxygen and nitrogen molecules in our upper atmosphere.
And they just knock them away.
Right. They transfer their momentum and knock the atmospheric molecules right off the planet out into deep space. Over a few million years, the solar wind would literally sandblast our entire atmosphere away.
Which is a terrifying thought. But that is exactly what our invisible magnetic shield prevents.
Yes. Because the solar wind is made of charged particles, it interacts directly with magnetic fields.
Right. Magnets push on electrical charges.
Exactly. So as this plasma stream approaches Earth, it hits the magnetosphere.
And the magnetosphere, just to define it, is this invisible shield or region of space around the planet where our magnetic field is the boss.
That's a great way to put it. Yeah, it's the dominant force out there.
So I love this analogy from the source material. It compares the magnetosphere to water parting around the bow of a ship.
That's exactly how it behaves. The magnetic field acts like a solid physical barrier. It forces the incoming plasma to split and just flow around the Earth, safely steering the vast majority of that deadly radiation right past us.
Okay, but I have a question about that. Because if the sun is constantly blasting us with this intense energy, and the magnetosphere is fighting this violent battle just above our heads, why don't we feel it? I mean, I walk outside on a sunny day, and all I feel is the warmth on my skin.
Well, you don't feel the kinetic impact because the invisible shield is doing all the heavy lifting. It's catching and deflecting those particles tens of thousands of kilometers out in space.
Oh, so it's happening incredibly far away.
Long before they get anywhere near where we live. The only solar energy that actually makes it down to the surface is the electromagnetic radiation, the visible light and the heat. The physical mass of the solar wind is blocked entirely.
Wow. And we know for a fact how essential this is because we can just look at Mars, right?
Yes. Mars is really the ultimate cautionary tale here. Billions of years ago, Mars actually had a liquid core, a functioning dynamo, a strong magnetic field, and a thick atmosphere.
It probably even had oceans of liquid water, right?
It very likely did. But, Mars is much smaller than Earth.
So it cooled down faster.
Exactly. Its core eventually solidified. And when the liquid metal stopped churning, the Martian dynamo died.
And the shield vanished.
The shield completely vanished, and without that protection, the solar wind just went to work. Over billions of years, it relentlessly sputtered away the Martian atmosphere until only that freezing, tenuous wisp we see today remained.
Man, that really puts things in perspective. It's a silent guardian. But the shield isn't completely impermeable, is it? Because occasionally, this massive invisible system actually lets us see it working.
It does, yeah.
And here's where it gets really interesting, because we get to talk about the sparks in the sky, the aurora.
The northern and southern lights.
Yeah. I mean, aesthetically, it's one of the most breathtaking things you can see. But from a science perspective, you're looking at something huge.
You're watching the Earth's magnetic defense system actively dealing with a massive influx of energy, yeah.
So how does deflected space plasma turn into glowing green curtains in the sky?
Well, it happens because the magnetic field lines aren't just a rigid bubble. When a particularly strong gust of solar wind arrives, like from a solar flare, it actually compresses the front of the magnetosphere.
Like pushing on a balloon?
Right.
Right.
And this forces the magnetic field lines on the night side of the Earth to stretch out, almost like rubber bands.
Oh, I see.
And eventually they stretch so far that they snap and reconnect.
And that snapping releases a ton of energy.
A massive amount. When they snap back, they act like a slingshot, and they funnel some of those trapped charged particles straight down the magnetic field lines toward the poles.
So they crash into the upper atmosphere.
Exactly, at the north and south poles.
Which is where I want to bring in a fun analogy. I like to think of this like a giant atmospheric neon sign.
Oh, I like that.
Because in a neon sign, you have a glass tube filled with gas, and when you shoot electricity through it, the gas lights up, right?
That's essentially exactly what's happening. The incoming solar particles are the electricity providing the shock. They smash into the oxygen and nitrogen atoms high in the atmosphere.
And the oxygen gets excited and glows green or red.
Right, and the nitrogen gives you those beautiful blues and purples.
So when you're standing out in the cold in Iceland watching the sky dance, you're literally watching the visible sparks of our shield catching the solar wind.
You're watching the shield work overtime, yeah.
But the fact that the aurora is focused at the poles leads to another wild realization. The magnetic poles are the anchor points for this whole system, but they move, don't they?
They absolutely do.
Because my compass points to magnetic north, but that is not the same as the geographic North Pole.
No, it is not. Geographic north is the fixed axis that the Earth physically spins around. But the magnetic poles, remember, they are generated by that sloshing, turbulent ocean of liquid iron we talked about in Section 1.
The chaotic outer core.
Right. Because the fluid is chaotic, the magnetic field it generates is also restless and chaotic. So the magnetic poles wander. They drift measurably every single year.
Which is just the surface level proof of that churning metal down below.
Exactly. Every little wobble in the magnetic pole up here is just a reflection of an eddy or a shifting current thousands of kilometers down there.
Okay, but this logically leads to a massive question. If the poles are wandering a few kilometers a year, what happens if we extrapolate that over, say, hundreds of thousands of years?
Well, eventually, they can wander so far that the entire field flips.
Flips, like upside down.
Yes. It's called geomagnetic reversal. The magnetic north pole and the magnetic south pole completely swap places.
Wait, so my compass needle would suddenly point toward Antarctica? Okay, let me push back on this a bit, because I've seen the disaster movies. Every time pole flips make the news, it's framed as this apocalyptic event. Like, the shield is gonna drop, we're gonna get irradiated, it'll be a mass extinction. Should we be panicking?
No, definitely not. If we connect this to the bigger picture, all those Hollywood doomsday scenarios just aren't supported by the science.
Okay, good to know.
I mean, we know these reversals are real. They've happened hundreds of times in Earth's history, typically every few 100,000 years. But it's not a sudden switch.
It doesn't happen overnight.
Not at all. It takes centuries, even millennia, to unfold. The main magnetic field begins to weaken, it gets very complex and messy, but the shield never completely disappears.
So it weakens, but it's still there.
Right. And even in that weakened state, combined with our thick atmosphere, it still provides enough protection. We can look at the fossil record, and these past flips do not line up with any mass extinctions. Life on Earth has survived hundreds of them without missing a beat.
Although, I mean, I imagine it would be a huge headache for us today with all our technology.
Oh, absolutely. A weakened field would cause massive problems for satellites, power grids, GPS. It would be an engineering nightmare.
But not an apocalyptic extinction event.
Exactly.
Okay, but this raises a fundamental question. If these flips take thousands of years and they happen over huge geological timeframes long before humans were around, how do we actually know they happened?
Ah, that is such a cool story.
Right. Nobody was out there in the Ice Age with a compass mapping this stuff. How do you measure an invisible force from millions of years ago?
It's all thanks to a field called paleomagnetism. We don't need human records because the Earth naturally records its own magnetic history in the rocks,
The rocks themselves.
specifically volcanic rocks.
Okay, let's break this down. How does a rock become a compass?
Well, it centers around mid-ocean ridges.
Let's define that really quick. Mid-ocean ridges are those massive underwater volcanic mountain ranges where the tectonic plates are pulling apart, right?
Perfect definition, yeah. As the plates pull apart, magma from deep inside the Earth rises up to fill the gap, and it creates brand new ocean floor.
Got it.
Now, when that magma erupts, it's incredibly hot.
Mm.
But crucially, it contains iron-rich minerals.
Like magnetic minerals.
Exactly.
Wow.
But because the magma is so insanely hot, the magnetic minerals are totally chaotic. They point in random directions.
So just jumbled up.
Right. But as the magma hits the freezing ocean water, it cools rapidly. And as it cools, it drops below a specific temperature threshold.
And the chaos stops.
Yes. Once it cools past that point, the magnetic minerals suddenly lock into place. They align perfectly with whatever the Earth's magnetic field is doing at that exact moment.
Oh, wow. So they basically act like billions of microscopic compass needles permanently freezing in stone.
Exactly. It literally creates a permanent barcode in the rock.
So it's
Yeah.
like the seafloor is a giant, incredibly slow tape recorder.
That's a brilliant way to describe it.
New lava comes up, records the magnetic north, cools, and then gets pushed outward as even newer lava comes up behind it.
Right. And so when scientists in the 20th century started measuring the magnetism of the ocean floor, moving away from these ridges, they didn't just find one magnetic direction.
What did they find?
They found alternating stripes.
Stripes.
Yeah. One stripe of rock where the microscopic compasses pointed north, just like today. But then a few kilometers further away, in older rock, the compasses were pointing south.
Because the field had flipped when that rock was formed.
Exactly. And this striped pattern proved not only that the poles flip, but it was the smoking gun evidence for plate tectonics. It proved the seafloor was actually moving and spreading.
That is just elegant detective work. The invisible field from a sloshing liquid core not only shields our atmosphere, it physically etched the history of moving continents into the bottom of the ocean.
It really highlights how deeply interconnected everything on our planet is.
It really does. Well, we've covered a lot of ground today. We started with the simple trembling needle of a handheld compass and traced it all the way down to the planetary dynamo of swirling liquid iron.
The giant engine under our feet.
We saw how that engine creates the magnetosphere, this invisible shield fending off the solar wind. We talked about how it paints the sky with auroras and how, over eons, it occasionally turns upside down, leaving its history frozen in stone.
It definitely makes you look at a compass differently, doesn't it?
Absolutely. The sheer scale of the mechanics keeping this planet habitable is staggering. But as we wrap up, there's one final thought I want to leave everyone with. And it builds on that cautionary tale of Mars we discussed.
Ah, yes. The cooling planets.
Right. Because if moving liquid metal deep underground is what generates our protective shield, what does that mean for the long-term future?
It's a profound question to mull over on your own. Thermodynamics dictates that all planets slowly cool down. Mars's core solidified and his shield died.
And Earth's core is cooling too, right?
It is, very slowly. It'll take billions of years for our dynamo to freeze, but looking outward to other planets in our solar system, or even exoplanets. If every planet eventually cools and solidifies, does every planet inevitably lose its unseen guardian?
And if they do, could humanity ever hope to live long-term on a world that has permanently lost its ability to deflect the stars?
It's a haunting physics problem, for sure.
It really is, but an incredible one to think about as we look to the future. Thank you all for joining us on this deep dive into the invisible force holding our world together. Keep questioning the mechanics behind everyday phenomena, and we'll see you on the next deep dive.